And I take this opportunity again to welcome you all to Physics Day 2024. Thank you.
Thank you very much. Hello, can you hear me? Is the mic okay? Thank you, Arunima, and I'm delighted to be with all of you on the celebration of physics. I'm very happy. This is the 5th installment of the same event, and it's a very nice idea to come together and hear about physics from a number of different people. I also want to thank Prasenjit, I think, who is online for suggesting this, and I'm very happy again to be with all of you. So I will I'll try to tell you a little bit about some of the ideas in a particular direction of physics that I have myself been working on. It can be broadly viewed as some kind of a quest. I think physics in general is a quest for understanding. You understand different aspects of nature, and this is a story about one such quest. Okay, so I like to sort of say that this quest, what I will do today is give you some kind of snapshots of, it's like if one of your friends went for a trek to the Himalayas and you came back and showed you some of the pictures. It will be a bit like that because I won't be able to go into, and I don't want to really go into all the details. So I'll try to just give you some sort of snapshots, and I want to just stay with that Himalayan idea a little bit, and just to give you a little philosophical introduction to the ideas I am going to present. So these are pictures of Kanchenjunga and K2. They are at two different extremities of the Himalayas. And in fact, if you think about it, it would not have been obvious to many people long ago in some ancient times that they were part of one, is it blurred a bit? I don't know. Network, okay, hopefully it will be fine. So it wasn't, I think, always probably known that these are part of a single mountain range. The people who lived near the Kanchenjunga, of course, saw the Kanchenjunga and many peaks nearby. They wouldn't have known even of the existence of K2, which is on the other end of the Himalayas. And similarly for the people who lived in the vicinity of K2. But these are some of the highest peaks, and there is Everest in the middle. And so what I want to say is that people had to map out the terrain to understand that these are all connected in one way. And these are some paintings from one of my favorite painters, Nicholas Roerich, of the Himalayas, who painted the Himalayas. And slowly people made a map of the Himalayas, and you can in the 19th centuries or so on, people really realized that there is a long connected range which stretches for several thousands of kilometers. But of course, nowadays it's very different because in some ways there are satellite images and you can directly see them. You can just open Google and you will find images which with your own, which are photographs from the sky of the whole mountain range. So why am I saying this? It's because I like to say that the laws of physics, our quest to understand them, has been of a similar nature. What are we doing when we try to frame some laws of physics? We are trying to find out regularities amongst very complex behavior. So if you look around the world around you, things seem very complex, right? And in India, it is particularly chaotic and often seems very difficult to understand. But how are you going to find some regularities and patterns inside this complex behavior. That is what science is about, and in particular the laws of physics treat the whole of nature as a universe, as a system to find patterns in. And what is quite remarkable is that we have been able to do that in precise mathematical language. So mathematics is a language which has helped us to capture these regularities in a very precise quantitative way, which you can then measure, you can experimentally check, you can observe, and realize that yes, there is a correspondence between our mathematical equations and the reality, and that we are able to understand some aspects of nature in this precise language. And that's what the laws of physics are. We learn when we are in school, we learn some laws. We learn Archimedes' law, maybe we learn some Coulomb's law, Newton's law. Few laws we learn. These are limited to Archimedes' law is about floating bodies. We learn some other laws, maybe Hooke's law about how springs extend, etc. So these are limited laws, but they were very important because they helped us to understand, capture some aspect about all floating bodies or all stretchable objects, and at least within a certain domain. And this has been how we have been piecing together the laws of physics. And we seem to have been able to do this even as we widen the scope of these laws. So one of the things, in a way, I'm trying to convey the kind of the philosophy or the scientific method, in some sense, how it has evolved. So initially people had these individual laws, but then people tried to widen the scope of these laws, try to explain more and more phenomena through some simple mathematical language. And in that sense, that's you may see why I'm trying to with that Himalayan idea. I mean, these are the different Kanchenjunga and K2 are like individual peaks, and you are trying to slowly extend your vision, your scope of your vision to these broader laws. And but one thing that has also happened as we have widened the scope is that sometimes to do that, we have had to also change our conceptual understanding of, sometimes it has required us to overhaul our understanding of what we thought. We have these precise laws, they explain things very well, but then you realize that at some point, and I will illustrate this, they break down perhaps in some circumstances. So then to be able to widen it to include those, you sometimes have to do a kind of a whole reorientation, and I'll make this a little clearer when I give some examples. But so this is how the process of evolution of scientific laws has happened. So as I said, the understanding in physics has come in this way that we do firstly a detailed ground survey, like all the people who studied the different parts of the Himalayas, and you discover simple laws like the ones I mentioned, Archimedes' law or Hooke's law, and so on. But then you start piecing together the terrain around the nearby peaks and try to obtain more general laws. So laws that will encompass more and more of these phenomena. And what, in a way, you're doing is to sort of broaden the scope so that you see how they're all connected into a single Himalayan range, so to say, a single range of mountains. All the different peaks, different laws are like not disconnected. They're all connected. They're all part of a larger understanding that we are trying to piece together. So I want to focus on two peaks in our understanding. So 20th century theoretical physics has made big advances in this project of widening our scope and broadening our understanding and connecting different ideas. And essentially, there have been two major pillars which were very revolutionary in 20th century physics. And these are the general theory of relativity, what I'll abbreviate as GTR, and quantum field theory, or QFT. And I'll say a little bit more about words. You may or may not have heard about them. But in any case, these have been very important pillars in our understanding of 20th century physics. And so the general theory of relativity has been very successful in giving us a theory of the cosmos and its evolution on the very largest scales. And I'll say something more about that. And quantum field theory, on the other hand, has captured the physics at the very smallest length scales. So you have these very successful descriptions, and I'll say more about them, but they are at two different extremities, like Kanchenjunga and K2. One is at the very largest scales, and the other is at the very smallest scales that we can probe. What are these scales? I will mention again. And what today's story, in a sense, or the snapshots, will be about trying to find the connectedness between these two peaks. There are, of course, many other things in 20th century physics which I will not be able to touch on. In fact, I often say the frontiers of physics are the very, very large, like in the cosmos, the very, very small, like those probed by particle physics, but also in the very, very complex, which is also something that we have learned quite a bit about. And in a way, quantum field theory often plays an important role even in that, or statistical mechanics, many of these other tools which even predate quantum field theory. But I won't talk about that peak or that frontier. I will mostly concentrate on these two, the largest scales and, so to say, the smallest scales. Though quantum field theory is a very versatile framework which includes even more. So, so let us start. So now that was sort of more philosophy. By the way, if you feel like asking questions in the middle, also please stop me. I think we can. It's the main idea is to have you people engaged. And if you lose me at some point, just stop me and ask me what I mean. So we'll start our story around gravity. And gravity is, of course, something we all feel. So even when you're a child, you know that you will fall down, you'll hurt yourself if you try to defy gravity too much. So this has been always with us, but it was not until Newton in the 17th century, 18th century, 17th century, that people understood gravitation in a sort of a more universal way. And Newton's law of gravitation, which you all learn in school, that was in a sense the first universal law. Universal in the sense I mentioned earlier, there were laws to describe very specific things, but Newton's law was a much bigger statement about the motion, the behavior of all massive objects in the universe, not only on Earth, not only in some corner of his apple tree, which you have a poster nicely of today for your t-shirts. It's not only restricted to apples and a small corner of England, but it is not only the whole Earth, but it describes the motion of all the planets. We have been sending spacecrafts, Mangalyaan, Chandrayaan, etc., all following the orbits determined by Newton's laws, combined with the inverse square law of gravity. But what is perhaps not often realized is that this was very successful, of course, at the level of the planets, the sun. So it was a big step when Newton realized that the same thing that makes the apple fall is what governs the motion of the moon around us and the tides around, on Earth, that are caused by the presence of the moon and the sun, and motion of the other planets around the sun and their satellites, etc. They were all captured by one law, one mathematical law. So that kind of illustrates how physical law has increases your understanding. You see a regularity, you see patterns. In fact, when Halley's comet returned, that was when Newton was really proclaimed as a genius, because he predicted that this object will come on such and such a time, and it did. So that was, of course, very successful, and people tested it in very fine detail all through the 17th, 18th, and 19th and early part of the 20th century. And they found it described things very well. And you could consider the perturbations of other planets, etc. And it was doing very well. But slowly people realized that there is a range of validity of this law. So this is an important concept that you should internalize as a scientist or as a physicist, that all these physical laws, they are very successful in a certain range of validity, a certain domain of validity. There is, when you cannot expect Newton's laws necessarily to be valid at all, in all possible circumstances. And it's important to understand when they break down. And that is very crucial, because that's what allows you to go beyond, to go to the next level, the next law that kind of subsumes Newton's laws, but kind of goes to a broader level. So it's very important to understand, where does Newton's law fail? We all know when it is successful, but when does it fail? It breaks down under two different sets of extreme circumstances. We now know by hindsight. Newton didn't know, and even wasn't very clear till early 20th century, but gradually has become much more clear, and we see it. We see observational evidence for that, Newton's laws do break down under two different sets of extreme circumstances. What are these circumstances? So the limitations of Newton's laws are one is when objects move very, very fast, when they are spinning very fast or moving very fast. And by what do I mean by fast? We now know that there is the speed of light as a sort of an absolute limit on at least so far, we know, limit on the velocities or speeds that objects can have. So when the velocities are comparable to the speed of light, are a substantial fraction, say half the speed of light or 1/3 the speed of light, then Newton's laws do not work. And there are systems in the universe where you see that, for example, pulsars are very spinning very fast. There are objects that are okay. So that's one. I mentioned two places where it breaks down. So just keep this in mind. One is when things move very fast. The second is when the densities become very large. And again, this is, maybe you might think the Earth is a very dense object, but that's like maybe a few grams per centimeter cubed. So it's not that much heavier than water and so on. But in the universe, there are objects which are much, much heavier. There are neutron stars. There are which in a way the pulsars are related to but there are in the centers of galaxies and many other places where the densities become very large. Then again, we see now that Newton's law is no longer accurate. It doesn't hold in the way we understand it. So Newton's law does allow you to describe a large part at his time the known universe was more or less the solar system. And of course, you could see the distant stars, but you didn't really know how much you couldn't really say very much about them. But it described all the phenomena, the regularities in the solar system. But as we have probed more of the universe, and now we can see some of these through varieties of telescopes and varieties of wavelengths and so on, we realize that this is a limitation. So what Einstein did and what the general theory of relativity did was to overcome, at least partially, as we'll see, these limitations of Newton's laws. So as Einstein writing down his equations, so his description of gravity, which the general theory of relativity is applicable at very high velocities also, when they are, so to say, relativistic, where the speeds are comparable to the speed of light. It's also quite accurate for moderately high densities, like in these neutron stars that I mentioned, which have actually, I think, a teaspoonful of neutron star weighs as much as the Earth or something like that. So it's enormously dense, you can see, by our standards, but it's you can, of course, you can imagine things, and there are situations which get even more dense. So in any case, Einstein succeeded in overcoming these limitations. And this is now an important part, that he managed to overcome these limitations not by just tweaking Newton's laws. He didn't just say, oh, we have to add one more extra term to Newton's laws. It's not GMM by r square. Maybe you have to add something 1 over r cubed or something. And that was not how Einstein realized that you had to go beyond Newton's law. What he did was to overhaul completely the very framework of describing gravity. So this is what I meant in the beginning when I said you have to sometimes conceptually reorient yourself, and together with perhaps increasing sophistication in the mathematical language. And this is exactly what Einstein did, because he tied up the description of gravity with the geometry of space and time. So this is not something people had really thought of. They assumed, I mean, everyone, we learn geometry, but they assumed that it was sort of a Euclidean geometry like you learn in school. Parallel lines never meet. Some of the angles of a triangle is 180 degrees and so on. But actually, mathematicians had realized that you can have more general geometries, and that mathematical description of more general geometries turned out to be very important for Einstein's description of gravity. So what he said was that space and time are not some kind of a passive stage on which all the physical events happened, because we normally think of it that way, that the space and time are there and then we are doing all our things, having a physics day, having a lecture, enjoying your fun time with your friends. But space and time are not doing anything in that. I mean, you sometimes, of course, feel you need more time or more space, but other than that, you don't really think of space and time as being active participants in whatever happens around you. But Einstein realized that that's not the case, that space and time are active participants. They respond to whatever is happening. So it's like you have a stage. The stage itself is participating in the drama. The stage is changing as the people in the stage are doing various things. So what seemed like a passive background now becomes an active participant. And how does it's somehow frozen again. Okay. So again, these are kind of caricatures, but the idea is that space and time, how do they respond? How does this background respond? It curves the space and time near it. So a massive object like the Earth curves the space and time quite a bit. I mean, not a huge amount, but enough so that objects that are in its vicinity, like the satellite, sense that curvature and move accordingly. And so the elliptical orbits that we learn about in Newton's laws now have a different interpretation in Einstein's picture, that they are in some ways the motion, the elliptical orbits are the motion of these planets or satellites in the geometry of the object they are rotating around, the geometry created by the object that it's orbiting. And the motion is in what is called geodesic, namely it is like the shortest distance along the path. So it's like the satellite is trying to move in the analog of a straight line path, which we would, if we wanted to go from here to there, we would try to go in a straight line. But when the geometry is curved, the notion of a straight line also becomes curved in some sense, and the straight line paths, so in this curved geometry, are these elliptical orbits. So that is the way in which Einstein reinterpreted Newton's laws, but actually realized that elliptical orbits are actually only a good approximation in the limit when things are moving very slowly or the objects are not too dense. Then it's a good approximation to use this elliptical orbits. And there are actually deviations from that. And that was one of the famous tests of general relativity, that the orbit around the sun had a slight difference from the normal elliptical orbits. There was a very tiny difference, and people attributed, and parts of it were due to some of the other planets and various other small effects. But there was a part which could not be accounted for, and it was precisely that extra piece that was predicted by Einstein's theory and was therefore a very kind of important test, that this picture, which broadens Newton's picture, is the more accurate picture. And now we see many things in the sky near neutron stars, orbiting binary black holes and neutron stars, that their orbits are very different from what Newton's theory would have told you, because they are orbiting at very high speeds, and they change the geometry around them so drastically that Newton's laws are terrible at approximating them. So Einstein's theory, by changing the way we think about geometry, think about space and time, helped you to overcome some of the limitations of Newton's theory. And as I alluded to, it's in a very different mathematical framework from Newton's. It was not just some small change to Newton's law that was made. These Einstein equations are equations for something called the metric, which is a measure of the distances and curvatures of a general space and time. So just like in electromagnetism, we have electric fields and magnetic fields. This is the notion that there is a metric field which measures locally, in a way, how different it is from the Euclidean flat geometry, where these would be just some constants. In this case, it is a non-trivial function of x and t, and that Einstein gave equations which tell you how to determine this object, this metric. Never mind all these indices, that just showing that it's a more general version of a vector, what is called the tensor. So Einstein's equations determine this metric in terms of all the matter and the energy. This is what I was saying earlier, that the space and time are determined, the space and time respond to the matter and energy in them, and the metric is determined by that, and that is what determines the curvature and therefore the motion of bodies in that space-time. Remarkably enough, these Einstein's equations reduce to Newton's laws for low densities and velocities. That's another important aspect of the physical laws of physics that you should keep in mind. That when you propose some new general law like this, and especially if it's very different from your original law, you have to make sure that in the limit where you have verified the earlier laws, namely Newton's laws and the solar system, Newton's laws work very well, that it should reduce to Newton's laws in some limit. It's the theory should be a generalization that has the ability to recover what you already know, namely for low densities and velocities, you get back Newton's law, and that's something you, if you take a course in general relativity, at some point you will learn how the Newtonian potential, the gravitational potential, can be viewed as one component of the metric, and the Newton's laws really is one component of the full Einstein's equations. And at low energies and velocities, you therefore recover what you already knew, but you now have a more general framework. So again, keep in mind this widening of the scope. So as I said at the beginning, this Einstein's picture of gravity in terms of geometry is a very successful description, which has been which has allowed us to describe the universe at the very largest scales. And now we are no longer, of course, tied to the solar system. We can measure, observe the universe to scales 1,000,000 times the size of the Milky Way, which is our local galaxy. So that's a huge step up, and to the extent that we can observe, apart from some of the hints of physics even beyond, we have a fairly successful description up to this very large scales of the universe. So these are various clusters of galaxies and so on. So you might think, oh, then we are done. Okay, we have understood things all the way to the largest scales. But no, Einstein's theory actually again has some puzzles. So it's like Newton's laws, in a sense, they broke down at some point. Einstein's theory also, in some senses, not complete, and that's has to do with the second aspect of our story, which is the fact that people realized not very far after Einstein's discovery, in fact, a mere 10 years later, that reality is at some level very different from the classical mechanics that, again, Newton had proposed for as a framework for understanding the motion of all objects, not only gravitational objects. And this came because of the existence of atoms, and the existence of atoms is something that would not be possible according to the classical laws of that were known at that time, namely those of Maxwell, which tell you that particles with charged particles like the electron would radiate if they're accelerating, and if you're in a circular orbit around a nucleus, the electron would have radiated all its energy and spiraled into the nucleus. So why do atoms exist? So this was a big puzzle, and so people resolved that and through this framework of quantum mechanics, and similarly, due to the other surprising aspect that light itself, which people had found many evidences for since Maxwell's theory that light is like a wave, people found a particle nature to light. So these were really things that needed to be brought together, and quantum mechanics did that. By the way, there's a little cartoon I found, which is a very nice idea of this duality that you see light is a particle. Can you read that in one way? Or you can also see light as a wave. But you can't see both at the same time, right? You either see light as a particle or light as a wave, and that's in a way captures that wave particle duality. So this, of course, is now the basis of all our modern electronics. So we are seeing this on touch screens and smartphones, computers, everything relies on our quantum understanding of matter. We wouldn't have semiconductors, we wouldn't have lasers, nothing without knowing the laws of quantum mechanics. And sometimes people say that 30% of the US GDP is based on quantum mechanics. So unless we had figured out these laws, we would never have had much of modern civilization as we know it. And this has been very important, not only for the GDP, but that in our understanding of the fundamental laws of nature at the very small scales, where we know that in addition to electromagnetism, there are these other interactions, the weak interactions of radioactivity that govern radioactivity, the strong interactions in the nucleus that holds the nucleus together. And we have come to a very good understanding of these other forces and are able to test them in these big colliders like in CERN. You can see this is the Geneva airport runway and this is the size of the collider. We are testing them to now not at the atomic scale. We are testing at 1 billion times smaller than an atom. And that's what in these colliders you can probe distances so small or energies correspondingly high, and it has been very successful. So we have on one hand the quantum mechanics describing very successfully the physics at the very, very small scale. We have general relativity describing things at the very, very large scale. These are the two frontiers I mentioned. But these two look very different descriptions. So if physical reality is really quantum mechanical, and that means that various things that we are used to in classical mechanics in describing things in terms of position and momentum, these are only things we learn in quantum mechanics, things which have only statistical outcomes. They are not things which you cannot precisely measure the position and the momentum. What you can measure is a certain statistical average depending on the so-called wave function of the state that you have. So these so-called classical observables are in some sense only have statistical outcomes. But then Einstein applied the classical mechanical framework to studying gravity in terms of this geometry or this metric field. It's a classical description like Maxwell's description. It's a more complicated equations, but still a classical description. Now, if you say that those objects are only statistically defined, the conclusion is that space and time now, apart from being curved, which was already something you have to bend your mind to get used to, you have to now maybe think of that space and time are only some statistically average notion. That's how do you make sense of that? That's and then you have to whenever you have these statistical outcomes really mean that there are fluctuations like in any statistics. So what are called quantum fluctuations. So how do we talk about that space and time are fluctuating and there are quantum fluctuations? What is the language to describe these things and which we can use to reconcile Einstein's picture with quantum mechanics? So you have these two very successful, very beautiful descriptions of nature, but they seem at some level very difficult to put together. And that's the quest for quantum space-time. But to understand that, I have to tell you where Einstein's laws also break down. So continuing, we get broader and broader laws, but then eventually we realize where they also break down. So Einstein's equations also break down, and that's a signifier that you need something beyond Einstein's theory, and precisely at the point where quantum mechanics would play a role. So in fact, just like Newton's laws broke down into different circumstances, limiting circumstances, Einstein's theory also break down into limiting circumstances. One is at very, very short distances, what is called the Planckian distance. A Planck scale is a length scale that is built out of the fundamental constants, namely Newton's constants, Planck constant, and the speed of light. It's a length scale which is about 10 to the minus 33 centimeters, very short, extremely short. I talked about a billion times smaller than an atom. That is 10 to the minus, about maybe liberally 10 to the minus 20 centimeters, you can take it. But this is 13 orders of magnitude, even smaller than that. So we are very far from something like that. And then at ultra high densities, remember I said Einstein's theory helps to overcome Newton's laws, the limitations at very high densities, but you can go to even higher densities, and then you see problems arising. And the equations, Einstein's equations themselves exhibit a signature of the breakdown. They develop what are called singularities, namely the equations have solutions which blow up, which go to infinity at some point or at some places. And so it is not clear how you can trust the equations there. So the Einstein's equations, in a sense, tell you that you can only trust them in certain situations, not in others. But how do you go beyond that? So now you might also take a viewpoint that maybe, but who cares? I mean, after all, why should I worry about? I have a fairly good description for everything I see. But in a sense, there are many good reasons why you need to have a good theory of quantum gravity, apart from just the pure idea of having a complete description, which is not just piecemeal. But we need so there is that need, of course, that we need to describe something that overcomes these limitations and a quantum theory of gravity. But more urgently, we needed to investigate the birth of the universe itself, or even to understand black holes, which we have been now observing. Because it may be, perhaps some of you know, but all the galaxies, everything that we see in the universe originated from very tiny quantum fluctuations at the very beginning of the universe. And that's the origin of the inhomogeneity. Oops. The inhomogeneity that you see in the universe. So this is a picture of the evolution of the universe, various things, galaxies forming, cosmic microwave. Now, at the very beginning, near the Big Bang, there's quantum fluctuations become very important. And that those quantum fluctuations are introduce an inhomogeneity. What was classically a very homogeneous background, there are small little bit more, little bit less. And when I talk about little bit more, little bit less, it's maybe 1 part in 10 to the 5, very small inhomogeneities, but that's enough in gravity for things to start clumping together and forming galaxies and clusters of galaxies and superclusters and so on. So that's been observed, these inhomogeneities. So this is a picture, I think, of the galaxies in the universe, and you can see it's not homogeneous. It is there are these voids and there are these filaments. And similarly, the microwave background, it's 3 degrees Kelvin to first approximation, but in 1 part in 10 to the 5, there are fluctuations, and there are hotter parts and colder parts, as you see by this color heat map. So to understand these precisely, you need to have a quantum theory of gravity. So that's so it's not something just about armchair kind of reasoning or satisfaction. So people have been trying to do this. There's firstly kind of an analogous situation that happened in electrodynamics. I alluded to earlier that it was Maxwell's electrodynamics that seem to be in conflict with the existence of atoms. And how did people resolve that? Maxwell's laws give a very good classical description. All the motors and everything that we have that give us electricity based on Maxwell's equations that you learn in your second semester, perhaps. But these laws also break down, as we have now familiar with. They have a regime of validity. Where do they break down? They break down at atomic scales, and that's one place we know it breaks down. And they also break down, maybe less familiar, but in very intense electric and magnetic fields also break down. Maxwell's equations break down, and you need to consider sort of additional nonlinear effects, etc. So again, Maxwell's laws, very good description for many things, but you have to go beyond if you increase your scope of your description. But in this case, there is a very successful theory that has overcome these limitations, and that's what is called quantum electrodynamics, developed in the 1940s and continued, and it is very successful theory. And so why not try to imitate that? That requires you to quantize the field corresponding to the interactions. In the case of electrodynamics, you quantize the electric and magnetic fields in a very specific way, and the interactions with the electrons or other charged particles. You might hope to quantize this gravitational field, which is this metric that I wrote down earlier, this maybe mysterious object, but it's a field in some ways like the electromagnetic field. But here we face the limitations of quantum field theory itself, which was very successful in describing weak interactions, strong interactions, and electromagnetic interactions, and in fact unified the electroweak into an electroweak interactions. But quantum field theory fails when you try to quantize this gravitational field in a similar way. At least till date, no one has managed to quantize it in a similar way. And that's maybe all right, because it's the gravitational field or gravity itself has a slightly different nature from the other forces, because gravitational fields have to do with the geometry of space and time itself, whereas quantum fields in a way assume that the space and time is fixed. It's like the passive backdrop, passive stage that I mentioned earlier. Quantum field theories kind of assume that passive stage and then talk about other fields on them, like electric fields. But if the stage itself kind of is fluctuating, that's something quantum field theory doesn't seem to be capable of doing. Quantizing geometry is, in a sense, even more subtle than quantizing electric and magnetic fields. And some of this failure is brought out by some of the puzzles that people unraveled about black holes about half a century ago. So black holes are, in a sense, one of the most striking predictions of Einstein's theory. They are formed when these neutron stars or very dense stars, they are no longer the gravitational force overpowers any other repulsive force that might hold stars together. I mean, the sun is held together by a balance of the gravitational force, which wants to pull everything in, and some radiation pressure, some general electromagnetic radiation pressure, the atomic, the pressure due to the constituent atoms. But at some point, none of that helps. And firstly, things can collapse into a neutron star. They can go even further, and that's what Chandrasekhar, Subramanian Chandrasekhar was very famous for realizing that. And the gravitational field is so strong, and the space-time becomes so curved that the light itself cannot escape from behind a certain region, which is called the horizon. You can think of it as a sphere of some radius, which is proportional to the mass of the object. So this was a prediction, but now we actually detect it through this LIGO detector, That's thicker. But we also see, so the LIGO detector, this is a simulation of these binary black holes and generating gravitational waves. And you can infer that these are black holes at the center. Similarly, from a different set of observations and about different system, namely there are black holes at the centers of galaxies, and this famous picture from the Event Horizon Telescope shows that. So black holes are now a reality. They are there. Many of them are there. LIGO detects almost like a few, like one per week or something, or even more. But black holes, therefore, form a very good theoretical laboratory for understanding quantum effects. What we measure so far has been the properties of black holes that Einstein predicted, the gravitational waves and other things about black holes. But you can try to understand the quantum effects of gravity through in the case of black holes, and Stephen Hawking was one of the pioneers in that. So Hawking discovered that if you try to describe black holes at the quantum level, you're forced to assign them a temperature. And something we have all learned in thermodynamics called the entropy. And this temperature and the entropy, there are, Hawking found, at least for large black holes, very precise expressions for them. This is for a spherically symmetric black hole, the Schwarzschild black hole. Temperature is proportional to the Planck's constant, so that's why quantum effects, how the quantum effects come in, and the Newton's constant G and the mass of the black hole M. Similarly, the entropy is proportional to the area of this horizon that I said, this region from which light cannot escape, and again, a fundamental constant. So these are very universal kind of law expressions. But the fact that they have temperature and entropy suggests that black holes should have some internal structure, because after all, only objects which have many atoms, like a bottle of water like this, have entropy or temperature. You don't assign a temperature to an electron or to a proton. So there's internal structure, and that in a sense conflicts with the description that Einstein's theory gives, namely that black holes are unique solutions of Einstein's equations. Also, there's a second puzzle. I mean, it's already puzzling that they have an entropy, but the form of the entropy is also puzzling. And that is that it is normally, if I looked at the entropy of this bottle, it will be proportional to the volume of the water in this bottle. In the language of thermodynamics, entropy is an extensive quantity. It is proportional to the volume, you may have learned. The entropy of gas molecules in this room is proportional to the volume of this room. But here, it's proportional to the area, not the volume, the kind of area of this region. That's very unusual. You don't have any other physical system in which the entropy is proportional to the area. So in some ways, that shows that the degrees of freedom in quantum gravity are far fewer than, even though they have some internal structure, that internal structure is a little more sparse compared to that in a bottle of water, because as you know, for a large object, the volume grows much bigger than the area. So it seems much the entropy, which is a measure of the degrees of freedom, I forgot to mention. The entropy is a measure we have learned maybe in statistical mechanics, some of you may have learned. Entropy is a measure of the number of degrees of freedom in the different configurations that the system can have. And the fact that it is much less than the volume signifies that somehow there are degrees of freedom, but they are fewer. So it's very different from some of the other forces. So if I had a gas of photons in a box, they would have an entropy proportional to the volume of the box. If I had a gas of some other neutrinos, etc., things which have strong interactions, weak interactions, their volume entropy is proportional to the volume. But in gravity, it's different. So that's where some string theory comes in, and I see that I'm quite. So I started maybe at 10:10 or 10:15, 9:15. I can go on for another 7-8 minutes. Yeah. Okay. So string theory, in a way, originated as I would say, it's a conservatively radical modification. It didn't undo things in the dramatic way in which Einstein overhauled gravity, but at the same time, it was somewhat radical modification of quantum field theory in describing objects, describing interactions in terms of sort of extended objects, like one-dimensional extended objects, like the strings, which could be open or closed. Yesterday, with some of you, I was describing some of that. So you consider the quantum dynamics of these extended objects, and it's a very constrained framework, even more than quantum field theory. It showed some promise in addressing some of the difficulties quantum field theory had with respect to gravity, namely if you wanted to consider the interaction of gravitons in quantum field theory framework, that was very difficult, but in viewing gravitons as excitations of this closed string helped you to understand, make sense of the scattering of gravitons, for instance. And so this is why people thought string theory had some promise in understanding a quantum description of gravity, but it had not, in the initial days at least, addressed what is this quantum space-time. And that has begun to change, and in a way, from the theory itself, there was one learned kind of a rather surprising thing that, and this is a development which has been unfolding in the last 20, 25 years, of string theory has managed to give a very precise proposal for how, for a large class of spacetimes, how they will behave at the quantum level. And the surprise is that in all these cases, the quantum gravity seems to be described by a quantum field theory. But I spent a good part of the talk telling you why gravity cannot be so easily described by a quantum field theory. So the surprise was that this quantum field theory is a description of that quantum gravity, but in one lower dimension. And how is that? So this is the proposal that was put forward by Juan Maldacena, Argentinian physicist. He made a proposal for the quantum behavior of a class of spacetimes. They come with a name called anti de Sitter or ADS. But these spacetimes are kind of generalization of the curved spacetimes. I told you, that there can be, you can have curved spacetimes in which the geometry is not that of Euclid. There are the so-called hyperbolic geometries. And in fact, if you have seen these paintings by this artist Escher, he had captured some of the very unintuitive features of these hyperbolic geometries. So this anti-de Sitter spacetime is an example of a hyperbolic geometry, but it's now space and time. So you can think of time, if it is in a vertical axis, you can think of, roughly speaking, you can think of it as like a solid cylinder with this, with the time in the vertical axis and each the different cross sections here being sort of hyperbolic spaces. So of course, I'm showing here space-time in two plus one dimensions, 2 space and 1 time. But you can have such spacetimes in any dimension. And the statement, the proposal, I said that the surprise was it's described by a quantum field theory. It's a quantum field theory that lives on the boundary of this. So namely just this surface, the 2-dimensional surface, which has the time direction and the, if you think of the cylinder, it's just the surface of the cylinder. As so you're describing gravity in the solid, in the interior of the cylinder, the behavior of gravitational gravitation of the quantum level in the interior through a quantum field theory that is on the boundary of that cylinder, on the surface of that cylinder. And this quantum field theory is not a quantization of that metric field. That's what people had tried and not really succeeded, but it's a quantization of other fields, apparently not at the first sight, not directly even related to the original quantum gravity question, but these are gauge fields like the ones that arise in electromagnetism. So the electric fields and magnetic fields that you learn are special examples of that arise from what are called gauge fields. You might have seen the vector potential in electromagnetism that has a gauge symmetry, gauge invariance. So there are the strong interactions and weak interactions. So similarly, these gauge theories. And so this quantum field theory is that describes this gravity in the space-time is one of these gauge theories. And there is a precise dictionary between the bulk, that means bulk, I mean the interior, the three dimensionals, the solid cylinder, and things on the boundary, that is the surface of the cylinder. There's a dictionary which tells you that if I want to study some quantum effect inside, I have to calculate this object on the boundary, on the surface. So there's a precise dictionary between what you would, what quantum observables you would think of inside and things that you can compute with on the boundary. And the boundary computation and calculations are based on quantum field theory, which we understand fairly well. So it simplifies our understanding of quantum gravity. And at the same time, actually, it has worked both ways. In fact, the gravity description, there's a limit where the inside can be described in terms of classical gravity, where the quantum effects are not important. And when that is the case, you learn many new things about the quantum field theory through gravity. So you learn both about gravity from the quantum field theory, and you learn about the quantum field theory from gravity. So both ways it works, and that's why it's been a very remarkable kind of development. And this is sometimes what is called ADS-CFT correspondence, or the gauge string duality. It's something that I have been working on myself. So one of the pictures that arise there is of this notion of this gravity being holographic. A hologram is something which captures a higher dimensional object in terms of a lower dimensional one, like on your credit card sometimes you see these hologram images, which on a two-dimensional, this thing looks three-dimensional. So it's a bit like that. This two-dimensional surface of this cylinder captures the three-dimensional inside. That's why it's often called the holographic kind of description. So in some ways, as I said, everything about the full quantum behavior of that space, at least for this class of spacetimes, this ADS spacetimes, is encoded in the quantum field theory. And this is a cartoon about that everything, in a sense, about the geometry is encoded in this sort of hologram here. And this hologram itself is made out of individual, it's a quantum field theory which has these individual qubits. So this is one of the things that people are deciphering, and this has actually led to some resolution of some of the puzzles that I mentioned. So the black holes in the inside of the space-time can be thought of as just quantum field theories at finite temperature, like a gas of photons in a box at some temperature, like a black body radiation box. Temperature is this Hawking temperature that I mentioned earlier. You also have a description of the microstates, the configurations that give rise to that area entropy. So that area entropy that I wrote earlier now follows because it's a quantum field theory on the boundary, and so it's that entropy of that quantum field theory is just proportional to the area. which is the surface. So it's one lower dimension. So that Bekenstein-Hawking entropy, as it's called, this expression for a black hole entropy, is very naturally fits in with this proposal, because it is telling you why the degrees of freedom are fewer. They are kind of only as if they are only on the boundary of this, or the surface of this space-time. So I'm now come to the end. So what have we learned? Well, I think that quantum gravity is probably holographic in nature. We can understand the black hole entropy in a sense microscopically through this, at least for a class of spacetimes. And this notion of space and time are in a way probably emergent in a classical limit, just like water in this bottle arises from many, many atoms. But when you just see the water, you don't realize there are atoms underlying it. So it seems like a continuous medium, whereas really you have, so similarly, space and time at some level probably are very discrete and emerge from as an emergent continuous description from a more fundamental description. For that, we need to decode this hologram better, and people are applying ideas of quantum information to do that, and it's a very interesting frontier. There's a question of how quantum spacetimes, other than the particular one that I mentioned, how do they behave? Again, people are trying to figure that out. So I would say what we have learned, so what is the current state of our understanding? This has uncovered very striking new facts about quantum field theories, which are strongly interacting. In a way, in addition to behavior of gravity, and in a way, it's the next best thing to having experimental evidence, because it makes predictions about theories which predate string theory, namely quantum field theory and general relativity, which are highly non-trivial and falsifiable. It lays bare the mechanism which for this connection, and which I think will be very powerful in many real-world contexts. And so I feel that in this 21st century, we'll see these two peaks, namely this quantum field theory and general relativity, the Kanchenjunga and the K2 will probably be linked together in a panorama. So I hope to see you all. I'll just leave you with something that Stephen Hawking